This is tutorial 6A question 5. In this question, we are given an LTI system with impulse response that is infinite. Although it's infinite, it is causal, and it is a geometric progression. We're asked to determine the output yn at steady state. So later on you'll this is important, given that this is the input, which is a tan, a sine at pi over 2n, as well as a cosine at pi radian per sample. And this is from minus infinity to infinity. The hint is given by this. We assume that the system is linear. Well, we know that it is linear because it's LTI. We're going to use frequency response at the digital frequency, and we realize that the digital frequency we are interested in is in pi over 2, as well as omega equals to 0 for this constant to calculate the steady state response. Let's draw the diagram. When we draw an LTI system, we typically just draw a block to say that this is LTI and Hn represents the impulse response. We are then asked to write y of n, and we are given x of n. Now the trick is that since we know that the system is linear, we can study each of these input individually. So we let x equals to 10 first, just a constant. So what is 10? It is actually 10 times cosine. What is omega? Omega is actually 0n. So basically a constant 10 can be viewed as a cosine with frequency radian per sample equals to 0. Why is this so? Well, 0 times any n is 0, cosine of 0 is 1, so 10 remains constant for all n. Now what about the output? You cannot use the convolution equation to solve it, because what happened is that xn lasts from minus infinity to infinity, and hn is also an infinite sequence. So if you try to solve it this way, you can't even pretend to try to make this sum works. So how do we solve it then? We use the frequency response. Remember that the frequency response is simply Hn, and we convert it by Dtft to h of omega. And h of omega is the frequency response. In particular, we are interested in finding h at omega equals to 0 for the magnitude and the phase. And when we have the magnitude and the phase response at omega equals to 0, we can plug it into 10. Of course, the question now is how to find h of omega. In this example, we know that h of n looks like this sequence, where a is half. Now we can use the z transform to find the z transform of h of n, which is h of z. And then by the lookup table, this is our h of z, and this is the region of convergence. Remember that we can convert h of z into h of omega simply by substituting z equals to ej omega. So we put z as ej omega, and now we have the frequency response. So this is a trick. We have simply used the z transform lookup table to convert our impulse response into its z transform, and which is called the transfer function actually. So these are all the names that you should remember. H of z is called the transfer function, h of n is called the impulse response, and h of omega is called the frequency response. Now since we have h of omega, all we need to do is to substitute for different omega, and we remember we're interested now for omega equals to 0. So what do we get? h of 0 is equals to 1 over 1 minus half e minus j 0, 1 over 1 minus half equals to 1 over half is equals to 2, and that is the answer. Basically, it has a magnitude change of 2 and the phase is 0 because this is 2 plus j0. When we convert to polar notation, the magnitude remains as 2, the phase is 0. So we come back to here and we say that the frequency response at omega equals to 0, magnitude changes 2, the phase is 0. So the output when the input is 10 cosine 0 n is basically the original input 10 times the gain, the magnitude gain, which is 2, remaining as the cosine 0 n with a phase shift of plus 0. So this 0 comes from here and this 2 becomes this 2 here. What about the original input? So the original input, let me draw a different color and let's be the 10, and this is the 10 for the input. So 10 remains multiplied by the gain at that frequency. The frequency is omega equals to 0 and the phase shift is also 0. So the answer, final answer is of course 20 cosine 0 n, but cosine 0 n is also 20. So basically when the input is 10, through the system the output is 20. And we can do again for the rest of the signal. So now what we need to change is we throw this away, the input. We now examine the input for minus 5 sine pi over 2n, and basically we want to find the frequency response at omega equals to pi over 2 because this is the frequency of the sine. We then plug in h of omega for omega equals to pi over 2. So let's go to the equation. So basically we are going to use this equation now. Omega equals to pi over 2. We substitute pi over 2 into h of omega, which is here in the yellow, or I should say green now. Omega equals to pi over 2. We work out this ratio of 1 divided by 1 minus half e minus j pi over 2, and we get a rectangle number which we need to convert it into a polar notation. In the polar notation, the gain is 0.894 and the phase shift is minus 0.4636. So what do we do now is we take the input, which is originally 5, we multiply by the gain, which is 0.894, the original frequency multiplied by n, and the phase shift is minus 0.463. I think I made a mistake, so this should be minus because the original input is minus 5. Now you can do the last one by yourself. All you need to do is that the last signal is, let's see, the last signal 20 cosine pi over n. So the amplitude of this cosine is 20, the omega is pi, so we substitute omega equals to pi into the frequency response. So it's 1 over 1 minus half e minus j, so the frequency is pi. We then work out the magnitude and the phase, and we substitute this magnitude gain here. 2/3. The original input is 20. The original value is plus 20 cosine. The original frequency of the signal, and now the phase shift is 0 because we see that h of omega at pi has a phase shift of 0. So the final answer is yn is equals to this 3 values. Now, we call this the steady state response because you'll realize that there is no transient involved. For all n, you'll always be run this equation describing it, and there is no transient, means nothing is dying, there is no decaying factor. Right, that's it. Thank you.